Now we'll be taking a look at spherical coordinates. First, we'll see how the spherical and cylindrical coordinates are related. Now, in this 3D rectangular coordinate system, we'll be taking a look at the triangle formed by the Z and the R and the rho with the angle phi. So we know that the sine is the opposite over the hypotenuse. That would be the R in the rho. We know the cosine is the adjacent over the hypotenuse. That would be the Z in the rho. And of course, theta is consistent in both of them. Now we'll take a look at the Pythagorean relationship in this triangle. R squared plus Z squared equals rho squared. We can solve this one for rho and use only the positive square root because rho is always positive. Likewise, if we take the cosine phi equals Z over rho and replace the rho with what we just came up with, we can do the arc cosine of Z over the square root of R squared plus Z squared. So these are the relationships for the spherical and cylindrical. And here's all of those put together on one slide. And I have this on a handout in another place. So if we wanted to find the spherical coordinates of this point in cylindrical coordinates, we take the rho equals square root of R squared plus Z squared, substitute, and simplify, and we get the rho. If we do the arc cosine of Z over, now remember the bottom is rho, and we end up with the arc cosine of square root of 2 over 2, which we probably recognize. And remember, the negative pi over 6 stays the same. Likewise, we could type this into our TI-89. Remember to use the angle sign on the second coordinate. And to go the opposite direction, from spherical to cylindrical, we'll use the R equals rho sine phi, substitute, sine pi over 6, and Z, substitute, cosine pi over 6, and theta stays the same. Now also remember that on the spherical coordinates, when you enter those into the calculator, you want to use an angle bracket on the second and third coordinates. So let's switch and look at spherical and rectangular relationships. Now we just developed these relationships from the triangle that we were using initially. Now we want to use this triangle and write the y and the x in terms of the r's and thetas. Now we'll take these and put them together by replacing the r in the bottom one with what r is equal to up at the top, and that gives us rho sine phi cosine theta. And similarly, we want to take the top one and this one, put them together the same way, replace the r in the bottom one with what r is equal to from the top. And so there are our three components. And we'll put these together in a little chart later. Now we're going to take this right triangle and write the Pythagorean relationship, r squared plus z squared equals rho squared. And in this triangle, we're going to write the x squared plus y squared equals r squared. And we're going to combine these two, like before, by replacing the r squared in the top one with x squared plus y squared. And so that gives us our rho is the square root of x squared plus y squared plus z squared. Now in this same triangle, the tan of theta is y over x, so that would make theta the arctan of y over x. Now this is an issue that we'll have to resolve when we do it because, again, the arctan is only valid in a couple of quadrants, and those aren't always the quadrants that we're interested in. Now, back in this triangle, we've got the cosine of phi is z over rho, and the rho was the square root of x squared plus y squared plus z squared. So we have a relationship now between the phi and the x, y, and z, where we can find the value of phi. So here's a chart, which is also on the handout, of all of those relationships. So let's practice converting this point to spherical coordinates. So using the equation for rho, substituting, squaring all of those and putting them together, we get our value of rho. Doing the arctan of y over x means we're doing the arctan of a negative square root of 3. Now, if you type this into your TI-89, you'll get negative pi over 3. Now, negative pi over 3 is in quadrant 4. The point that we're given, negative 2 and 2 square root of 3, is in quadrant 2. So we're going to have to modify our angle so that it's an angle in quadrant 2 that matches this. And that would be 2 pi over 3. And we can just type this in. And so there's our point conversion. And likewise, this is what it would look like on the TI-89. Now, converting points is pretty easily handled with the TI-89 calculator. However, converting equations is a little bit more complex and takes a little bit more thinking than what a calculator can handle. So let's see how we can convert this equation from rectangular to spherical coordinates. First off, we're going to take the x squared plus y squared plus z squared part of the equation and replace it with rho squared. Then we're going to take the z and replace it with rho cosine phi. Now this is what we would come up with when we make those two replacements. And this is where our thinking skills come in. Rho is the distance from the origin out to points along the surface. Now if rho was a 0, then that means we'd only have a dot at the origin, which is not much of a surface. So we'll assume that rho is not 0, meaning we can divide both sides of the equation by rho. And so by doing that, we get rho minus 4 cosine phi, which we add 4 cosine phi to both sides, and we get rho equals 4 cosine phi. Now we could take something like maple and type that in spherical coordinates and see what the graph looks like. Now going the other direction, we'll take this point and convert it into rectangular coordinates by replacing the rho and the phi and the theta. We get the value of x, and replace the rho and the phi and the theta to get the value of y, and replace the rho and the phi to get the value of z. And here we have the same thing typed on the TI-89. And like I said earlier, converting equations requires a little more thinking skills. So what I'm going to do on this one is remember how I developed the relationships. The sine of phi from an earlier slide was r divided by rho, which makes the cosecant, the inverse of that, the reciprocal of that, which is rho divided by r. So we're going to take the cosecant and replace it with rho divided by r. Now you can see we can divide out the rho's, multiply by r, and come up with r equals 4. And earlier we saw r is equal to the square root of x squared plus y squared. So we'll replace r with the square root of x squared plus y squared. We'll square both sides, and we come up with this equation. Now remember, this is 3 dimensions, so x squared plus y squared equals 16 would be a circle in the xy plane with a radius of 4, but going infinitely in the z direction. And so here's our graph.